Okay, I'm going to go ahead and start on this next example. Inspired by the "Does background music influence what customers buy" example, a statistics student decided to investigate other ways to influence a person's behavior. Using 60 volunteers, she randomly assigned 20 volunteers to get the red survey, 20 volunteers to get the blue survey, and 20 volunteers to get a control survey. The first 3 questions on each survey were the same, but the 4th and 5th questions were different. For example, the 4th question on the red survey was, when you think of the color red, what do you think about? On the blue survey, the question replaced red with blue. On the control survey, the questions were not about color. As a reward, the student let each volunteer choose a chocolate candy in a red wrapper or a chocolate candy in a blue wrapper. Here are the results. Do these data provide convincing evidence at the alpha equals 0.05 level that the true distribution of color choices are different for all 3 types of surveys? All right, so we're going to do an entire state plan do conclude process here. All right. So starting out, we're going to say H null. H null is that the true distributions of the color choice in candy are the same for people who chose the red, or people who had the red survey, blue survey, or control survey. Okay. I don't think we really need to say true, actually. You can. It's not wrong. I don't know why I crossed it out. Actually, color choice in candy. This is a weird problem. The distributions of color choice in candy are the same for so for all 3 of the surveys that were given. This is state. HA Okay, so there is a difference. Or the 2 distributions, or these distributions are not the same. However you want to say it. I probably said more than I needed to, honestly. All right, so plan. We need to name the type of test we're doing, which is a chi-squared test for homogeneity. Homogeneity, I don't know if I really made this point clear, but hopefully you know what homogeneous means, the same, right? So a test for homogeneity is a test that determines whether the distributions are the same or not. That's why we call it the test for homogeneity. Whereas whenever it was just one group, we were doing a goodness of fit to see if our fit, our data, our statistics were fitting what the claim about the population was. So hopefully the differences in the names are making sense, because the other one we're going to do is a chi-squared test for independence, which is pretty similar to the way that we do this one, but it does differ based on the information that's given. So conditions, random. They randomly assigned 20 volunteers to each survey. 10% here, this is a controlled experiment, so we don't have to check 10%. We only check 10% when we're sampling. Expected counts. I'm going to go ahead and say, all right, so expected counts greater than or equal to 5. We're going to do that in the calculator when we run our test anyways. And so when I'm going to leave a little bit of space right here so I can do that. Let's see, I'm going to need 6. Since I have 6 counts here, I'm going to have 6 expected counts. So if I kind of like, I don't want to take up too much space because I have to do Dewey and conclude down here. Let's see. And we could do these by hand like I did on that on the video I just did for the, hopefully you've already watched it, for the checkpoint you were supposed to have done in class today. I'm just going to leave this here so it lines up to that one, so I feel like that's pretty, I mean you can write like RS, BS, CS, and then over here RC, EC. But you don't have to write those. I think if they're in the same order, that pretty well says. And if they're all greater than or equal to 5. So in a second here, I'm going to do that. So on my do step, because if you remember from class, we can get those from the do step. It's faster. All right, so we want to show our degrees of freedom. You always want to give your degrees of freedom anytime you're running a T or chi-squared test. So degrees of freedom are row minus 1, so 2 minus 1, we have 2 rows minus 1, we have 3 columns minus 1, so our degrees of freedom is, this is 1 times 2, so degrees of freedom 2. So then chi-squared, we'll just do chi-squared equals, and we'll start that in a second, and then we need to give our p-value. Those are the only things you need on here. Degrees of freedom, chi-squared, and p-value are what you should have written on your do step. And I haven't written it yet, obviously I haven't calculated it yet, but I can't even start writing it because I don't have the expected counts yet. So in the calculator, I'm going to put, remember we have to do this with a matrix. And so I'm going to go ahead and say, what do I want to call it, candy? So I say candy and then control the matrix button and then the matrix button again. I'm going to need a, let's see, 2 by 3. So 2 rows, 3 columns, and then just enter my numbers in. Oh, didn't mean to hit control, meant to hit tab. All right, so my matrix is in there. And then I run my test just like we've been doing with the other ones. So 6, 7, 8, because that's the chi-squared 2A test. Okay. I'm going to go ahead and expand out my expected value matrix. So remember I hit var, and I want this one, stat expected matrix. And so my expected values are here. So notice that these 3 are all the same, and these 3 are all the same. The reason that that happened here is because they have the same number in each category. And so if they have the same number in each category, and they're all in the same row, then remember, like if, so how did we do these by hand? We did them by hand on the previous page. Oh, no, on the, when we did these, we did row total times column total divided by total, or table total. And so if we did that, if these two are the same and this is the same, then obviously they give you the same numbers. So anytime your sample sizes are the same, then all the expected counts in that category are going to be the same. So these three are the same, these three are the same. Anyways, just something to note. And so when I start to write my chi-squared, I know the calculator gives it to me, but I'm going to write out just the first term at least. So 13 minus 8.667 squared over 8.667 plus ... equals, and then I'm going to just grab whatever the calculator gave me. 6.651 or 652. Let's do 6.65. And the p-value from the calculator, 0.036. It gave me 0.035944. That's good enough. Okay, so I'm just going to draw a line here and do conclude. All right, so what do we conclude? Well, our p-value is smaller than the alpha because we were given an alpha here. It's the one we use anyways most of the time. So since our p-value of 0.036 is less than alpha, oh, I usually just write the symbol, oh well, you can write the symbol, of 0.05, we reject H null. There is evidence that I should say distribution. Dang it. And I like broke my whiteout a second ago. Just having a rough time. Sorry, guys. Okay, can't do this. Oh, fixing it. Okay. Yeah, this sucks. All right. They're the distributions of candy color so that the distributions of candy color choice are different for the different survey types. I should say the different survey types. Anyways, okay. Questions? No? Okay, great. So whenever we do a follow-up analysis, we're going to be using the calculators for these tests. I see no reason to do these by hand most of the time, like unless it's just to understand where those numbers are coming from. So for the most part, we're doing these in the calculator. What we want to do is, you'll notice whenever I chose that VAR here, there were a lot of things to choose. We're going to look at the component matrix, which is this one. It says comp matrix. So and we're going to look at the individual components and see which one is the largest, and then we'll be able to see if it was larger or smaller than expected. But here, let's look. So if we look at the component matrix, we can see that this is the largest one, which would have been the red survey with red candy, right? And so that had the biggest impact on our chi-squared test. So like basically to conduct a follow-up analysis, and hopefully you got a little bit of this from the textbook, it's when your results are statistically significant, you want to dive a little bit deeper and see what is it that's affecting the chi-squared statistic the most. And the way you do that is by looking at this component matrix. The fact that that one is the biggest is telling us that the red survey and red candy choice had the biggest impact on our chi-squared test statistic. So the observed count was larger than what was expected. And you can get that from here too, right? It was expected was 8.667, and the observed was 13. So let me just finish writing something here, and then our follow-up analysis is gonna be based on what I was just showing you in the calculator. So. Okay, I'm sorry. I guess I didn't really totally explain what a component matrix is. So we're going to use this. We're going to write this at the bottom, but I want you to see. All right, so when I was writing down how we would calculate the chi-squared statistic by hand, if I do that, so if I say 13 minus 8.667 squared, and then divide that by 8.667, do you see that that number is the same as the component in the spot in the component matrix? That's what the component matrix is. It's the individual calculations that we add together to get the chi-squared statistic. Each individual observed minus expected squared over expected, that's what shows up in your component matrix. So that's why the largest one tells you the biggest difference, right? And then because these are always going to be positive in your component matrix, you have to look back to your expected counts and your original survey and see which one is bigger. Because we would have gotten that same value in the component matrix had the expected been 13 and the observed been 8.667, because since we square it, it's going to make it positive. And so anyways, that's what the component matrix actually is. So I'm going to write the follow-up analysis. So I'm going to copy down the component matrix from here. I think that actually was my screen just went blank. I'll just leave it at 0.51. The next one, 0.039. Okay, so that's our component matrix. And I write what I said a second ago. This one's the biggest, so that tells us that there's and then You want to also state if it was larger or smaller than expected. The observed was larger. Okay, so I'd like you to go ahead and try to do checkpoint 3. I'm just going to put up the answer at the end of class tomorrow, or sorry, at the beginning of class on Thursday. If you have problems with it, you can come see me, because we still are going to do the chi-square test for independence on Thursday. We're probably not going to get through all of this. I might skip some of it with you, because the chi-square test for independence is very similar to homogeneity. It's like the way that you complete it, it's just the scenario that you would see when you have to do it might look a little different, if that made any sense at all. So anyways, I'll see you Thursday. Come see me if you have questions. Thanks.